Good. So I'd like to point out my collaborators as well, Cengiz, Alaettinoglu, and Chia-Chee, Kuan, who concentrated more on the routing side. I did more the jitter measurement side. What this talk is about is some measurements we've done on a transcontinental Tier 1, U.S. transcontinental Tier 1 backbone, beginning with measurements of jitter. That was our primary measurement, but in fact we observed a number of anomalies, and we, as a second step, began looking at routing protocol packet traces in order to understand those anomalies and to analyze them. So I'm going to talk about what we found, and the purpose of doing this was that we believe that these networks really are working very well and can support delay critical services. We wanted to measure the jitter so that, because the amount of jitter that you have determines the volume of delayed critical traffic you can handle and the latency that you can provide to the customers. But we make the observation that there are some problems that need to be fixed. So it's equally important to talk about what this talk is not about. Some members of the program committee were concerned this could be a vendor bashing talk, and it certainly is not. It's not particularly important, in fact, even which vendor we're talking about or which ISP we're talking about, because I believe that these problems or problems like them are likely to be seen on many of the networks that are out there. They're fairly rare problems, as I'm going to talk about, so the networks are working mostly pretty well. And what we really want to do is look more closely. So I do want to point out this is actually a collaboration with the ISP and the vendor to try to analyze and find these problems. I'm making the title of this slide intentionally provocative, make a statement about the state of the network, having reporting on data primarily from observations of one network. In school, it was only the psych majors who were allowed to extrapolate from a single data point, not anybody in real science. But in fact, we have now just recently begun tests on another network. We have 3 days of testing on that network in Europe, and the results are similar. Again, most of the time it's great, and there are a few funny things that occur. So, as I said, the backbones perform fairly well. There may be problems on access networks, but for the most part, backbones work very well. We looked at, we have like 15 weeks of data that we've collected. For several of those weeks, about half, we found that availability was 99.99%, so that's also already very good, and that the jitter of packets that we, even counting those that were lost, the jitter is less than 1 millisecond for 4 nines of packets. The rest of the packets, TCP tolerates very well the occasional delays, and so that's why, to a large extent, if you're mostly concentrating on TCP traffic, you may not care or you may not have noticed or looked closely to see that these problems are there. But there are problems, and if we want to move on to tighter SLA requirements, then you'll have to look at them. The other observation about the state of the net is that routing is perhaps strained, but has adapted with various tweaks and such to handle the growth of the network over the past several years. The routing is really an area that we're concentrating on here for the problems. So I think operators have a pretty good macro level view of this state of the world using the kinds of tools that I've listed here, but I think most are not looking more closely. And if we want to go from 4 nines to 5 nines, then we have to find the more subtle problems which require a deeper understanding. If we want to get to tighter service level agreements for voice over IP, virtual wireless services, VPNs, that kinds of things, we need to see what's happening on a very fine time scale and over long periods of time, and that's basically what we've been doing in these experiments. So as I said, the basis of the experiments is jitter measurement. We installed test hosts, PCs in POPs in San Francisco and DC, and make a parenthetical comment here that we've been very careful about those, the security of those 2 PCs to make sure that they're not going to get hacked. These are connected directly to core routers with gig ether links. Those routers have have OC48 network between them, and we're sending a fairly small level of traffic at 1 megabit per second, but because we use varying length and exponential distribution of the interval between packets, we really are testing something that covers more of a range of packet conditions, and the randomization avoids synchronization with other periodic events that may be in the network. So as I said, we've collected data for about 15 weeks, 15 periods of 5 to 7 days, and then we bring that data back and analyze it. Because we only have a measly T1 line to our home base, it takes about 24 hours to bring the data back, so that's why we can't collect data continuously. Our yellow, kind of funny yellow. Our test setup is, as I said, a couple of PCs installed in the 2 POPs. The PCs are running a program called TG, which I want to thank Barbara Denny from 3Com for providing that to me. It actually was developed some 10 years ago in the research community. We've done some augmentation to it to allow it to work with a sequence of timestamps in the packet, measuring different points along the path. And in particular here, the driver inserts a timestamp on the way out, so it's as close as we can get to the network with very small delay. And then over on the input side, the gig ether interface, sysconnect interface, actually timestamps the packets as they go by the Mac level chip and passes those timestamps to the driver, which converts it to the right time space and inserts it in the packet. So as we're collecting the data, we get timestamps that have an accuracy, as I say on the title there, of about 20 microseconds. We're running the data in both directions at the same time so that we can see effects that, well, when there's a loop in one direction, for example, you can see what's happening in the other direction, that kind of thing. So after we pull the data back, then there's various kinds of analyses that we do. Inter-arrival jitter is an easy way to get a quick overview. That's looking at the difference between the spacing at the transmitter and spacing at the receiver, but that doesn't show everything because it turns steps into spikes. So we also look at those hours that have interesting phenomena with packet loss and delay, and then for the interesting hours, we graph absolute jitter. And what I mean by absolute jitter is the time difference between the timestamp, just for a single packet, between transmitter and receiver. Now, if you think about that, those 2 clocks are not going to be synchronized. We could use NTP to synchronize the clocks, but there's a risk that NTP's clock adjustment algorithm is going to cause noise in the data, cause something that will interfere with the jitter measurement. So we don't do that, and we just compensate after the fact for the drift in the clock. So here's my first graph. The y-axis here, as I was saying, I'm labeling as jitter. What that is the delay from the transmit timestamp to the receive timestamp, with 0 set to be the minimum, 0 set to be the point where most of the packets lie. So when you take the bulk of the packets, the 0 point for that bulk of packets. Now, this mostly looks like a red line. Some of you may be able to see that there's a few red spots above the line, but I put it up in this form to say that there are 70 million points in the red line, and there's a few points that aren't on the red line. There's the points for those who couldn't see them before. So 99.99% of the packets are in the red line, but there's clearly something else going on here at around 20 milliseconds, and in fact some below and above that. And what that is that's going on, we determined, is losses due to ARP cache timeouts. So because the way ARP is implemented, the cache is flushed and a packet is held until the ARP response comes back. There's a 20 millisecond scheduling factor in there that causes the band at 20 milliseconds. But you don't really have to do that. Instead of flushing the ARP cache, the right solution is to, when the ARP timer expires, go ahead and send the ARP request, but continue using the ARP cache entry until such time as there have been n attempts at the ARP request with no response, and then you can flush it. So the ARP still all works fine, protects against addresses being stolen, all that stuff, but you don't have to lose packets. So at each one of those points where there was a delay, there was also probably a packet that got lost, one or two. What we've done as a workaround is to put in permanent ARP entries, but clearly that's not anything that's workable on a large scale. So we're calling on all of the vendors. I think all the ARP implementations that I know about are wrong in this manner, so it needs to be fixed everywhere. So some of you may have noticed that there were also a couple of points on the graph with negative delay. What does negative delay mean? Well, only that these are packets that came in faster than the nominal 0 point, where most of the packets did. And if we look closer at one of those, what that really was is a shift for a short period of time. This is about 40 seconds at the low level there, and you can see there's actually a couple of shifts up and down. This is shifting due to rerouting to a different path. There's several things you should notice here. The first is that there isn't any period of outage. There isn't any period of outage at the beginning of this. So this is a rerouting that didn't really need to happen. That is, the route change wasn't because the link really failed. Second interesting thing to note is that the shift is downward, which means that the alternate path is faster, is closer geographically than the primary path. I don't know if that was by design or not. It works okay. It doesn't create a problem, but it's unusual, or not what I would have expected initially. And the third thing you probably noticed is that there's a bit of a sawtooth pattern there. And so a close-up look at that shows that it's got a period of 2.3 to 2.4 seconds and a height of about 500 microseconds. In fact, we were able to do a test in the lab, the vendor lab, just a couple of days ago and determine that what this comes from is the OC12 ATM interface on the router that's presumably in the SAR processing. If you compare the result for an OC48 packet over sonnet link, then all you get is the little bar down at the bottom, like 10 microseconds. So this is, from my personal opinion, yet another reason not to use ATM. There's some fuzz in there. There's some fuzz in there that's the real jitter, the points that aren't sort of on the line or down at the bottom. So after the ARP problem was fixed, then performance was really very smooth. This is another test week after the ARP problem was fixed. In this graph, there aren't any points off the line there, except that then something kind of bad happened. There were a couple of shifts, but you can see here that there's a spike that goes off scale. So if I zoom out so you can see the full Y direction, it's actually 7 seconds of delay that some of the packets experienced. The bottom line here is you still need to think 70 million packets down in the bottom line there. So that even though the line is now thin, it's still got most of the packets in it. And even though this looks bad, these I can't draw the lines thin enough. The pixels are not thin enough to give you a real image of what the density of this is. This is happening over a period of 9 hours. So let me zoom in on the x-axis, and you see that in fact there really are, even though there's a lot of spikes there, they're not that dense. Zooming in even further, here's one of those spikes, that one same spike. Again, remember that there's a bunch of packets in the horizontal line, then there's a period of time when we receive no packets, and then we receive a whole bunch of packets all in one short period of time. And continuing to zoom in, this is what it looks like in that bunch of packets. It's zipping up and down a lot here. The height of this, again, is 7 seconds. The width is about 240 milliseconds, so you can see that the packets are massively out of order. Now, if I take each of the little spots there is a packet. If I take the line and instead of drawing the line in the order in which the packets were received, draw the line in the order in which the packets were transmitted, you can begin to see what's going on. I have called these things blender events, and because that's the impression that I got out of it. Tornado might be another word. You see that there's a bunch of packets on each line going down. And I'll tell you more about what we learned about those lines in a moment. The packets are sort of randomly spaced on the lines because of the random spacing of our transmission. There aren't actually any packets lost in this bunch, but there are some, as I say, that are 7 seconds old. We didn't want to believe that this was a routing loop because routing loops aren't supposed to happen. That's what the protocols are designed to protect against. But we couldn't really figure out what it might be in our end systems either. So we tried another analysis, which is looking at the cumulative bits received, cumulative megabits received. And normally this would be just a straight line, like following the first blue line there, if everything's going smoothly. But here what happened is we had a period of about 7 seconds where no packets, those packets are entirely gone. 1,172 packets were lost. And then the next 7 seconds worth of packets were all squeezed together and came in one bunch at 25 megabits per second. Since the 25 megabits per second is not our link speed and not our transmit speed, then we conclude that's not something we could have done from the end system. It's got to be somewhere where our packets were gathered together with somebody else's packets. And through further analysis of the routing, we determined that what's going on here, and this is the same blender again, a little narrower, is that the packets are in fact going in a routing loop. If you count there are 31 lines, and that corresponds to a loop of diameter 2, an initial TTL of 64, and a normal arrival TTL of 2. So the ones up at the top have just about used up their TTL, and there's another line above that, except those are gone because their TTL expired. Looking at another blender, this one happens to be 4 seconds tall. You can see an artifact that was on that one as well, that the slope is changing as it goes down, and what that represents is that the packets are decelerating as the loop gets longer and longer. It takes more packets to build up in the loop, and the queue builds up. So, as I said, we didn't want to believe this was a routing loop because that's not supposed to happen, so we implemented some additional monitoring of the network. We added, in addition to the TG traffic sending and receiving, we're monitoring with TCP dumps so that we can capture the TTLs on arrival. And more importantly, we're doing monitoring passive peering with ISIS, passive ISIS peering with the router that we're connected to collect all of the ISIS routing packets. We dump all of those to disk, and we're doing a trace route every 5 seconds. This is from both directions so that we can see the direct evidence of the routing loops and collecting that to file as well. And as I said, we're getting a lot of data, about 20 gigabytes a week for this. Since we've put all of this extra measurement with the routing in place, there have not been any more of these big blender events, but there have been some micro blender events, like this one, which has a shorter period of time of about 6 seconds instead, or 5 seconds, and only a few packets, but we can tell from the shape and the other characteristics that this is still the same thing going on. Here, these are the TTLs of the packets that arrived. Again, there weren't any that were lost, but the next line up of TTL next line up of packets had their TTLs time out. The spacing is not uniform here, again, just because that's the spacing between the packets as we transmit them. So, why do loops happen? Most of you know how the routing protocol works better than I do, but just to review the things that can go wrong, the way the protocol is supposed to work is we detect topology changes and flood those changes everywhere, compute an SPF on the changes to know what the new routes are that we can use, and all of that is supposed to be consistent within propagation time. It's all supposed to flood around, and there aren't supposed to be any persistent loops. But if the flooding doesn't happen in time, then we can get in trouble. And so we saw some specific problems that caused that. This first problem is a failure to properly time out and ignore LSPs that have a lifetime of 0. That is, LSPs that are no longer being used, no longer contain information, get marked with a lifetime of 0. The churn that you see here is that the problem was that the lifetime 0 LSPs would clear out the record of the LSP that was there before, but the other LSP was still out in the network because of timing delays. It would show up and reinstantiate itself, and then the lifetime 0 LSP would also be flooding around. It would come in and replace that. So the routes that were in that LSP would be coming and going over and over again, and you see that it's a massive level of churn. The limit here on the top graph, the line is at 9 there or so. That's really only limited by the fact that 10 LSPs per second is the rate limit on delivering the LSPs to our test host. This is as observed at the test host. So basically, a lot of the time it's sending us LSPs as fast as it can. The blue line on the bottom is if you subtract out all of the churn from this LSP, the lifetime 0 flapping, the ones that were really there, and in fact some of those probably shouldn't be there either, but you see that first off, the real churn is much less than the fake churn due to this problem. Now this problem had already been fixed in a later release by the time we had observed this, and that later release was already scheduled to go in place on the network, but it was, at this point at least, still causing trouble. So if you have all of that churn, all of those LSPs that need to be fed through the network, but you have rate limits on how fast they can be forwarded, then you can get some fairly substantial delays. The y-axis here is in seconds, so it took 160 seconds. If you look at the little diagram on the right there, we have an LSP that's originated at the router in DC. It's sent at approximately the same time to our test host attached to the router in DC, and then sent out across a few hops of the flooding topology for ISIS across the ISP network to the router in San Francisco where our other test host is connected, and then forwarded by the router there to our test host. So we look at the sequence number of that LSP in both places and timestamp when we receive it in both places and get a difference of 160 seconds. So that means that topology change was seen differently on the two sides of the country for a period of 2 minutes. And a routing loop could persist for that period of time because of that inconsistency. So an explanation of the kinds of loops that we've seen, and in fact we did, the blender example I showed you lasted about 14 seconds. We have also seen loops that persisted up to approximately 2 minutes. The explanation is that there was too much change to be communicated for the rate at which the LSP rate control would allow. We had the setting, as it says here on the backbone as it stands, is 4 LSPs per second. The important thing is to match the update rate allowed to the amount of churn that you, or the amount of change that you need to communicate. So there's delay both in communicating the LSPs and rate limits on how often the SPF calculations are done, which both can cause the databases to be inconsistent. Any topology change, here we had some problems from fake topology changes, but any topology change can cause a problem. For the blender events we see are for the path that's between our two test hosts, and in particular we were seeing apparent transitions on the link between the router and the test host at the DC end, which weren't really true, but occurred because that reachability was moving from one LSP to another, back and forth, and between the time that it was taken out of one and put into another, it appeared to be gone. That combined with delays in communicating that switch across the network so that that pair of packets might get spread in time is one way that the loops can form. And that problem also has been fixed already and is in what was already planned to be put into the network. So these problems will both go away, but there are likely to be others. Here is an example of what we suspect is a routing loop on another path, not directly affecting our own, since our packets were able to get through. But in this case, you see that the height of that hump is about 340 milliseconds. That's a similar height to the diameter of the blenders that we saw before. So what we suspect is happening in this case is that there's a routing loop affecting some other path. Our packets flow through the same set of routers and are experiencing, therefore, the queues that built up from that routing loop. In this case, the queues actually build up enough so that some of our packets are lost, as indicated by the blue lines down there, 1, 2, or 3 packets in a row that are lost. So this can cause problems on a variety of networks. Question?
Steve, going back to your previous slide, I don't remember there being any rate limiting in either the ISIS or OSPF spec, other than rate limiting the number of time or the time between reorigination of the same route. If you were to just have that sort of time limit and not a rate like 4 LSPs per second, wouldn't you eliminate that problem?
Yes, so you're talking about the protocol itself, I assume.
Yeah, in other words, if you implement the protocol itself without adding the extra knobs,
right,
or without doing something like mesh groups.
Right. So in fact, let me address that in a moment on the conclusion slide. Yes, you're right. That's what really needs to be done, is to look at those timers. So I've shown you several problems here. I want to wrap up with a slide that shows that most of the time collecting this jitter data is very boring. This is an example of one of the weeks, and there are several others like this. In this graph, there aren't any spots, so if you see any red spots on this one, you should see your optometrist. On this graph, we have 69 million packets transmitted over this period of 5 days. There were 0 packets lost. These are packets between our 2 test hosts. 0 packets lost, and 100% of the packets arrived within 700 microseconds, relatively speaking, of when they were transmitted. There's a constant propagation delay across the country that we're subtracting out. So mostly it's working very well. The backbone jitter is quite low, and for the backbones, now again, I'm not talking about going between backbones or talking about access networks, but for the backbones themselves, congestion is not a problem that we need to solve. There are routing problems that we need to solve, other anomalies we need to solve, but efforts towards trying to provide low delay services by attacking congestion may be misguided. There are several events that we do need to eliminate in order to have the service to get to from 4 nines to 5 nines level of service that we want to achieve. Some of those are simple ones like the ARP that I mentioned, and in fact the vendor in this case has been looking at that also for a while. So I want to again poke the vendors, and not just router vendors but host software vendors as well. We entered this as a PR in the FreeBSD database, and maybe we'll get around to working on it ourselves. Both hosts and routers need to fix that problem, but also, most importantly, needing to fix some of the routing problems. And so it really is timer settings like this quarter second per, or 4 LSPs per second, quarter second between LSPs. That timer setting is just too small for allowing the necessary number of LSPs to get through. I think that in the routing, as I said, it's handling the current scale, but it has had to be tweaked to get there. There have been a number of operational emergencies that led to putting in various kinds of rate limits and other protection mechanisms to keep CPUs from melting and other things. But in the meantime, there have been software changes to fix a number of those problems, implementations of things like mesh groups. And everyone's afraid to go back and look at the timers again. But if you want to get from the 4 nines level to the 5 nines level, you're going to have to understand these problems better. So we've been working on a couple of networks, as I mentioned. This data is primarily about one network. We've begun experiments on another network. We're interested in looking at some more networks, and so I'd like to hear from you if you are interested. But even separate from what we do, I ask you folks to look at the timers again, reconsider the design of the routing timing that you have on your network. In addition, there is room for improvement to more robust timers. We had a talk a couple of nanogs ago about reducing the amount of time spent on SPF calculations with incremental SPF, and there's more that can be done with protecting still against churn, against excess LSP traffic, but not in a way that harms the traffic that needs to get through. If you're more specific about which source you rate limit. And there's some more ideas there. Those are beyond the scope of this talk and maybe at a future nanog. So as I said, we are interested in hearing from others who would be interested in doing testing. There's my email. Feel free to send me an email or find me afterwards and we can talk more about it. So other questions?
Steve, I remember how these timers got put into a specific ISIS implementation. It came out of trying to do a full mesh in over an ATM backbone by a particular provider. And what happened was the network melted down. So in response, we got mesh groups. We got all these timers which are in addition to the specification, in this case, are getting us into trouble. So the thing for the providers to do is to be aware of this, not build full mesh, and not try to turn these timers on because they cause these persistent loop problems.
Right. Right. Things that used to be protection mechanisms are now biting you, so you have to consider them.
Well, I may be able to speak to the first point Curtis raised. This is BJ Gill, Metro Media Fiber. Nobody used mesh groups, Curtis. They were there, they didn't work. We didn't use them. We used the mesh of meshes to get around the timer issues. The other thing which I've seen before and which people seem to be harping on is reduction of timers. And because the implementations have gotten better, which may be true. The implementations have gotten better. The thing is that what we are dealing with here are very large, loosely synchronized databases. And our current schedulers of all router implementations that we are aware of and that we use in the backbone are run to completion router scheduling, which leads, if you turn the timers down too much, which leads to well, meltdowns. We've been there. It sucks. We don't want to go there again. So till the actual scheduling in the kernel of the routers is not run to completion, we are a bit afraid of turning timers down too much.
As I mentioned, that there may also be some ways to improve through the use of incremental SPF calculations, the amount of time that it takes, and attack that side of the problem as well. But that is a good point. Okay.
Thank you. Our last talk this morning is on the web agenda, but not on your printed agenda. I'm pleased to introduce Steve Bellivan, who's going to talk to us a bit about route filtering.
see if Mr. Bill's operating system will wake up here for me. Work. Okay. In some sense, my name shouldn't be on this talk. This is work mostly done by two co-workers of mine, Jennifer Rexford and Randy Bush. No, there's not a typo on that last email address. PSG.com address will work for Randy. Anyway, I don't think I have to tell this group about the traditional stance taken on prefix filtering by Verio, with Randy as one of its proponents. And the question has always been, what does it cost an ISP to filter as aggressively as Verio and some others do? Finally decided to sit down and actually measure it by taking a look at some BGP dumps and analyzing them. So we took some well-known BGP tables, the Telstra internal view from May 15th. Telstra is known for doing very little filtering. Route views from the University of Oregon, the RIPE multi-view, and a routing table from a Verio customer. Since that latter presumably represents an extreme of filtering. And we applied various filters. So one thing we did was we threw out anything longer than /24. We also went to the routing registry's smallest allocation sizes in the /8s. Start by cleaning the data, first removing the Martian filters, the 1918 addresses, the inter-exchange addresses, and so on. This gives the baseline reachability, things that we should be able to reach. Remove prefixes longer than, successfully remove first prefixes longer than /24, all prefixes in A space longer than the registries allocate, and the same for B space, then the same for C space and addresses greater than 206. Below 206 there's too much chaos, so we didn't even try to filter that. So what the legend is going to show on these tables is the number of prefixes removed at this stage, the prefix count after the filters applied, the count of /32s, that's to say possible endpoint hosts, which have become unreachable, and the proportion of baseline addresses that was reachable originally after we cleaned out the Martians and so on, but no longer reachable after this filter is applied. So when we look at Telstra, after we throw away the stuff, we just apply the /24 filter, we lose about 1,800 hosts. That's 0.000002% of the possible reachability. You apply filtering, throw out the stuff with A's, you start cutting out more prefixes. You end up, if you apply the most stringent filters with a routing table about 30,000 small, about 30% smaller than we started with, and you've lost 0.003 for hosts, about 3.8 million potential hosts on the internet. Not very many hosts by doing this filtering, and you get by yourself a 30% reduction in the routing table size. University of Oregon shows very similar numbers. Again, the most extreme filtering is 0.003, about 0.3% of internet hosts. Verio customers, the interesting thing, here is, you do see some loss in Verio. The reason is that Verio does not filter its own customers' longer prefixes. Again, the RIPE data, all these charts will be up on the web. There's no point to trying to read these numbers to you. Some warnings if you want to try to apply filters like this. Published boundaries can be wrong. For example, RIPE's allocating /20s and 62/8, whereas the policy statement says they're allocating /19s. When we looked at the lost prefix list, that stood out. We went and checked and changed our filters for the experiment. APNIC does not document at all what their allocation policies are. Also, these results are fresh out of the oven. This is a very late-breaking result. We're still changing some of the filters in our analysis Friday and Saturday. So there could certainly be bugs in this analysis, taking some quantity of salt. Now, if we assume that multi-homing is a major cause of the redundant announcements, and certainly that was the message from Jeff Houston's talk at the last IETF meeting, some of the other talks we heard there, well, these redundant announcements are people trying to engineer how we send traffic to them. In other words, the filtering techniques we're describing maintain reachability for most of the internet, but defeat those desires for redundancy and traffic engineering that for people generating these announcements. Well, is this good or bad? To paraphrase Sean, why should the rest of us allow you to consume extra resources on your routers when you're not paying us for that service? You know, why should an ISP have routing table entries caused by some other customers of some other ISP trying to improve their reliability? If you want space in the routing table with some ISP, pay them for it, is about what it boils down to. It's not clear that you have to go quite as far as these filters illustrate. If you go look back at the numbers, the majority of the benefit comes from the Class A and Class B filters. In terms of somewhat more than half the reduction of the routing table comes from Class A and Class B filters. The majority of the unreachable prefixes come from the Class C filter. So maybe just the A and B filters is the sweet spot in terms of minimizing unreachability while maximizing the gain in routing table space. Where to go from here? The discussion of the taxonomy of prefix coverage and filtering and so on. The Tomain box last IETF. It's a mailing list, tomain@shrubbery.net. If you're looking for ways to multi-home without exploding the size of the routing tables, look at the multi-6 working group and the IETF. In the meantime, these results suggest that filtering aggressively is probably a good idea. There's a bunch of useful URLs. In particular, the first URL has got the list of lost prefixes, the ones that were not reachable in these routing table dumps if we applied these filtering rules. The allocation boundaries to the extent that they're published, and this presentation. Question?
Was there any attempt to figure out a better percentage estimate of the number of hosts that are actually active on the internet, which you'd lose connectivity to?
No.
Okay, because it seems that 0.003 is a little bit low because, you know, we don't know what the distribution of active hosts is in those prefixes versus other prefixes. But
well, as I said, we tried looking at the maximum amount that was reachable by routing announcements, assumed they were all 100% populated, and saw what we couldn't reach after we did that.
Hi. Jeff Houston's conclusion usually is that CIDR isn't working and we shouldn't be doing it anyway, and everybody should get their own prefix of whatever length, and it should be portable. And I just wanted to ask you, based on your findings, whether you believe CIDR is working or not. I know you've pretty much already said it, but I feel the need to.
Yeah, CIDR, what Jeff's number showed was that CIDR was breaking down for people who really wanted the multi-homing and reachability. And one conclusion from this is you don't lose much baseline reachability if the backbones are really working well. And maybe the last talk tells us, at least in some sense, they are. Maybe you don't need that. And it's a question of who's paying and who's benefiting. Ultimately, I think there is going to be a strong push for multi-homing. We have to go solve that problem. The trick is to solve it in a way that doesn't put the cost burden on the wrong people. Yes?
Just to slow it down, I'm Joe Damas. I work for Drive NCC. I wrote Drive to 11. It's actually correct. What you were saying there on Saturday is an ISP splitting their allocation into smaller blocks, which they are free to do. So that document is still trustworthy.
Okay, great. Other questions? Great, thanks. You can reach us all on the net.